Welcome to another session of EI Live for K-12 students and educators, brought to you by the Earth Institute at Columbia University. My name is Cassie, and I'm the director for the Office of Education and Outreach, and a big part of my job is to bring our scientific research to different audiences. For those of you who aren't familiar with the Earth Institute, our core mission is to foster a greater understanding of the science behind sustainability and the climate crisis, and what we as global citizens can do. Experts that make up the Earth Institute include earth scientists, economists, lawyers, specialists in public health, and business and policy experts. The Institute is actually made up of more than 24 research centers and several hundred people who collaborate across many different disciplines and schools at Columbia. So today is actually our last session of EI Live K-12 for the 2019-2020 academic year. And we're excited to bring you our final session featuring Christopher Zappa of Lamont Doherty Earth Observatory, which is the largest research center that's part of the Earth Institute. Chris is going to help us understand how he's using unmanned aerial vehicles to study climate change, from the Pacific Ocean near Fiji all the way up to Coastal Village in the Arctic. We're going to be using the Q&A box for today's session and not the chat box. And this is where you can type questions for our presenter throughout the presentation and use it to answer questions that he may end up having for you. We'll monitor the chat box the Q&A box throughout the session, and we'll be sure to get to all of your questions. Once the session's done, we'll share a link with everyone who registered for the event so that you can access the recording later on when it's posted to YouTube. So without further ado, here's Chris.
Thank you, Cassie. Everyone can hear me, right?
Yep, we can hear you. Great. Thank you.
Okay. So as Cassie mentioned, I'm going to tell you about my research, my group's research at Lamont Doherty Earth Observatory, using unmanned aerial vehicles to study climate. And specifically, I just wanted to acknowledge a lot of this work has been funded by or supported by the Schmidt Ocean Institute. That'll be the first part that I talk about. And then the latter part in Alaska was supported by the Gordon Benny Moore Foundation. So this is a satellite map of the ocean temperature. And you can see in the equator, the ocean is much warmer than it is at the poles. And we are going to study this first region here, down in the southern equatorial Pacific, near Fiji. Here's Fiji right here, and here's this region we're going to study. You can see it's really warm water. We want to understand some of the processes that cause this water to become warmer, and why it would warm faster than other places potentially. And then we're going to kind of cruise up here, maybe I'll show you how this water mass makes its way eventually up to Alaska. And so here's this other location here in Alaska, and we'll look at how this how the sea ice is impacted by this warming water, and how that sea ice impacts the local indigenous community. So first off, we're going to zoom out. Here's Fiji right here. Here's Australia, here's New Zealand, and here's Alaska up north there. But we're going to focus on Fiji. And this first part of our work was done aboard the RV Falkor. Falkor is a private ship run by the Schmidt Ocean Institute, and we were working in and around Fiji. Near Fiji, there's lots of other islands. So here's the Fijian Islands. There's also Tonga, Wallis and Fortuna, Tuvalu, the Solomon Islands, Vanuatu. There's a whole host of islands that we were migrating around and studying the oceans in and around all these islands. And I just want to play a video that kind of describes the overall project and what we were trying to do out there. And then I'll come back and go through kind of some highlights that I wanted to discuss on. But I'll just play this now. You should be able to hear my voice over.
Why do we study the ocean? To put it simply, because the ocean drives our climate. This is a story of discovery, of how we observe the ocean from large scales to small scales, from coarse satellite imagery to ultra-high resolution surface maps. Our team from Columbia University is here aboard the RV Falkor to understand how the ocean is changing on a multitude of spatial and temporal scales, to observe how the ocean's ecosystem adapts and survives in a changing climate. The ocean is a very dynamic environment, and our method for making measurements needs to be equally dynamic, to react at a moment's notice. The Air to Sea story starts and ends with a map. From a low-resolution satellite map with a scale of hundreds of kilometers to a high-resolution map of microturbulence with a scale of millimeters. What's really exciting is how we get from one to the other. This is when the UAVs come into play. Deploying these autonomous aircraft, each equipped with specialized sensors and equipment, we're able to map a very large area efficiently and with considerably greater resolution than the satellite imagery.
A few days ago, we crossed over a very large pumice patch, and it was about 10 miles from the ship. We decided it was interesting enough to go send everything over there, so we picked up all the other scientific equipment, SPIP and Sniffle and the catamaran, and we hightailed it over to the pumice patch where everything got thrown back in the water, and we were able to map that out from the air while all the other scientific equipment on the ship and floating around the ship were able to capture that data as well. You wouldn't have never known that patch was just 10 miles away and a valuable scientific target.
Thanks to our ability to act dynamically using real-time data, we tracked down pumice, which was likely to be the remnants of an underwater eruption near Tonga in August of 2019. The data we collect at times like this, such as thermal imaging and hyperspectral color imagery shown here, allows us to understand the effect of surface material, in this case the pumice, on sea surface temperature.
Hi, my name is Una, and this is our infrared radiometer. It's one of the instruments we have mounted on the ship, and it gives us very high-resolution imagery of the sea surface temperature. So on the computer, we're able to see a 3 by 3 meter field of view of the sea surface temperature, and in that view, you can see all sorts of processes happening. Convection cells bringing relatively warm subsurface water and disrupting the cool skin, eddies, waves breaking, sea foam. They all have different temperature signals, and it's all very clear in IR imagery.
Altogether, this data helps us build up a transformational view of the sea surface microlayer in groundbreaking detail, one which will eventually allow us to understand how the ocean and the atmosphere interact and how the ocean's ecosystem adapts and survives in a changing climate.
That was a kind of a nice overview of what we were doing out on the in Fiji or near Fiji. We were studying how surface slicks, surface accumulations of material are impacting the heating of the ocean. So we were using the UAVs to track down where these patches were. We would go over there with the ship, put all our equipment in the water, measure the response of the ocean to these surface slicks and accumulations of cyanobacteria or pumice, and then map out a larger area with the UAVs. So we were doing a number of stations around Fiji. You can see here the cruise track. We started in Fiji and went up kind of the northeast, and came back down south, and then kind of went back towards Fiji. But you can see we did around 30 stations to track these surface accumulations, materials. And this is what it looks like up close. So there's two pictures here. Here's this is trichodesmium. It's this kind of floaty, very kind of, I don't know, dirty looking surface on both locations here, this surface film. And here you can see it's very calm relative to this rougher water to the right. So with both calms the water, but also allows more heat to be absorbed. And this is what it looks up under a microscope. So there are these long tendrils. I'm not really a biologist or microbiologist, so I would refrain from asking me questions on that. But we do know that there's much greater abundance of these at the surface than there are just a few meters below the surface. And this is what it looks like from a satellite. So on the left, you can see those long tendrils of this trichodesmium or the cyanobacteria. And then on the right is a map of the chlorophyll. But you also see on the right that there's a lot of white in the image from the satellite. And that's because there's a lot of clouds typically. So one of the benefits of using UAVs is we can still map out this large area underneath the clouds and see where this trichodesmium or these cyanobacteria patches occur, and then what their impact is on the upper ocean. So we were using the UAVs here, and we have surface buoys here that measure the ocean temperature very precisely, autonomously throughout the day. And we deploy both of them from the Falkor. So we put everything in the water, as we mentioned in the movie. The UAVs flying around. Here's our mission control inside the ship, where we can control the UAVs, we can track where everything is, and then kind of tell the ship where to go and where we want to go with all the other equipment. Here's an image from the UAV flying around the ship up to about 50 nautical miles away from the ship. We can go pretty far distance away from the ship to look for things. And then once we find something, we take everything out of the water. We sail over there with the ship and we put stuff back in the water. So here we're putting this surface drifter back into the water, and here's this surface slick of cyanobacteria, or trichodesmium is the name. And we're able to measure now what the response is of the ocean to this surface slick. And this is a picture from the UAV, just how extensive it is. So you can see it goes off into the distance here, pretty far, and there's a significant accumulation on the surface. And it's very variable as well. So even though we can look in different locations with the surface measurements, the UAVs give us a much better idea of how expansive it is and how variable it is, which gives us a better idea of how much ocean heating is occurring. So here's a map of the ocean surface using the UAVs. So on the left is the actual hyperspectral, so the visible picture of the ocean. And on the right is the temperature signal of those same patches. So here you can see two big, long patches of trichodesmium, one here on the top here and one here on the bottom. There's lots of little tendrils and sinews that go along with them. And in the temperature, you can see these warming events that correspond directly with this same cyanobacteria in both locations. And you'll see some warming, but you also see some cooling adjacent to that warming. So there's more than just simple physics going on, much more complicated that hopefully where we will get to understand using these measurements. And this is
Chris, I'm just going to interrupt because we've had two questions come.
Sure.
Sorry, Chris, can you hear me?
I can, go ahead.
Yeah, we've had two. Okay, great. We've had two questions come up. And they're related to this particular slide, and I think at the previous slide. So how much pumice did you find, and why on this particular slide are everything represented in rectangles?
Okay, that's two good questions. So how much pumice? That's a good question. We found, do I have that image up here? Hold on, let me get over here. Pumice is not on here. Okay. We would, in terms of volume, we didn't really do volume measurements of the pumice. We would take samples of the pumice, understand what it makes, corroborate that it was pumice, and then use the UAVs to kind of get an idea of how expansive it was. So it would expand, it would extend for, kilometers, tens of kilometers of these patches, these rafts, we'll say, of pumice. Here, this is cyanobacteria, what I'm showing here. And you can see here that these are about, kilometer scale and even longer of these patches of cyanobacteria. And the rectangles in each of these images are snapshots from the camera on the UAV. And they are kind of using the motion of the aircraft and its position. We're able to map all these images onto the ocean surface and build this larger mosaic, we'll call it, of the ocean surface. So those are individual snapshots from the cameras that we then patch together as a mosaic. Hope that answers their question. So the next, so now that once we find those patches and we have our little drifting buoy in the water that measures the ocean temperature, we're able to look at the response of the ocean temperature to these patches. So on the top here is probably one of two graphs I'm going to show, but this shows basically that as there's an increase in this trichodismium or the cyanobacteria on the surface, we see an increase in the ocean heating. And what you'll see here in the ocean, so here's the temperature of the ocean going up, and this kind of lighter orange area here, this is what models predict the ocean warming to be based on the measurement, all the measurements we made. And this is the difference between what the actual measurements show versus what the model predicts. And basically this is the impact of what the cyanobacteria trichodismium has on the upper ocean heating. So it's very significant. In this case, over 0.5 degree increase in the temperature when you have this trichodismium in place. So those are the kind of things that's what we're kind of studying in Fiji. And so we're using the drones and these drifters on the ship, mapping it out over large areas and looking at the response of the temperature of the ocean. Why would we see more warming in this region? And it takes a lot of people to go out to sea, both for the ship and for the engineers and for the technicians and the scientists. So there's a whole group of people that it takes to get this done. So now we want to zoom out. So the ocean is warmed up, and we want to zoom back out from Fiji. So here's Fiji on that satellite map of ocean warming. And we want to, now we want to study we're also studying how this ocean warming is impacting, or changes in climate are impacting indigenous communities in Alaska. And how would, say, this ocean water get to Alaska? And it's much more complicated than I'm going to describe here, but I'm just going to show that if we're here down in Fiji, you can have this south equatorial current going to the west, and then it kind of crosses the equator and it goes east along this equatorial countercurrent. Then it could come back to the west on this north equatorial current, go up to Kuroshio, which is it's like the Gulf Stream of the Pacific Ocean. And then it could go across the North Pacific Current and eventually get to the Alaska Coastal Current. And this is where the warm water enters into the Arctic Ocean. And that's what we are interested in Alaska. I see a little question there.
Yeah, we've got 2 questions here.
Probably a good time to look at those, I guess.
Yeah, so if you'd like to, so I think so the first question was, how do we know the direction of causality?
The direction of causality. So is the question, if you're asking about the direction of causality of the cyanobacteria warming the ocean? What, I'll answer that question, I think, is the easiest.
Okay.
So if you don't have slicks on the ocean surface, there's less absorption. There's just a natural ocean absorption of sunlight into the ocean. And typically that'll absorb over the, say, 10 meters to 100 meters in the ocean, depending on how transmissive the ocean is. So if you're in a deep ocean and it looks very blue, you can get the solar energy can penetrate very deep into the ocean, and you get warming in the top, say, tens of meters to 100 meters. If the water is if you're in coastal areas where the water is less clear, you may have absorption of the sun in the top few meters, say 5 meters, 10 meters. And in regions like what I was just showing, where you have cyanobacteria, it was showing that basically a lot of the sun is absorbed right near the surface, so in the top meter. So depending on how much of this material there is in the water, it'll affect how deep the sun penetrates and how much where the warming occurs in the ocean. So it can either be concentrated right at the surface, or it could be mixed deeper into the ocean. Hope that answers the causality question.
Okay.
And then
Thank
I see
you.
the question on.
You see the other one? Okay, great.
That's a bigger climate question than I would say, but a general answer is that higher winds over Africa are going to generate larger windstorms. So I don't know. I don't know the details of the atmospheric impacts and how that impacts the climate or the weather over the Sahara. But it definitely, if there's changes in climate, you could have stronger winds potentially, and that may impact how much sand is blowing off of the Sahara. So yeah, I'm not exactly an expert on Saharan dust. So we're going to zoom out from Fiji and zoom in up to Alaska. And we're going to focus on this region right here called Kotzebue. This is Kotzebue Sound. This is the Bering Strait. And there's Russia over here to the left. In this project, we are bridging scientific and indigenous communities to study sea ice change in Arctic Alaska. And the name of the project is Ikagvik Sikakun, and this is Inupiaq for ice bridges. So many of you probably know that have heard that the ice in the Arctic is thinning over the past 30, 40 years. And this has consequences for local communities. So it could both impact coastal flooding and erosion. It could also impact the marine mammals and habitats for polar bears. And this may impact traditional hunting and subsistence living of local communities. So the goal of this project was to, one, understand the ice dynamics and how it was changing in a warming climate, but also how to bridge scientific and indigenous knowledge to study these changes of sea ice. And then how does this impact sea ice loss, ocean life, and land mammals? And there were kind of three components to the study. There's a scientific component to understand why the sea ice is retreating. There's a community component to develop partnerships between scientists and local residents, not just the indigenous community, the elders, but also the broader indigenous community. And also a legacy to keep this project going on into the future, to work in community-based collaborative science. So as I mentioned, we're in this region here. This is Kotzebue Sound, right there. And a big part of Ikavik cocoon is the co-production of knowledge. And this is our team on the left here, our advisory council of elders. Here's me and some of the PIs on the group down here. And here's some of the graduate students and engineers on the project. So what determines ice transport processes in Kotzebue Sound? So one thing, so setting the stage, this is what the Kotzebue Sound typically looks like. It's typically ice covered in April. And we want to understand when does this open up? When does it melt, Kotzebue Sound? Because that impacts the indigenous community's ability for their subsistence living and their traditional hunts. So this is what it looked like in the same time frame in 2018. So it opened up much earlier than normal when we were up there studying it. And the same time in 2019, it opened up much earlier than normal as well. So if we zoom just out a little bit, and we look at what the typical years of sea ice concentration were for the kind of all the Arctic. So this is before, so this is basically from in March when we have the largest extent of sea ice. So you can see most of the Arctic and the Bering are covered in sea ice. More recently, you can see there's less sea ice in the peak in the winter than normal. That's 2018 in green. And then 2019, you can see even less sea ice than normal. And you can see the Kotzebue Sound right here is opened up significantly and earlier. And then this is a kind of a time lapse of how that sea ice then melts over the course of the next 2 months from April through May and June. And so you can see that over the last 20 years, it's decreased significantly during that melt period. And 2018 wasn't any different, or not much different than previous years, except that it started a little earlier. And as I mentioned, that warm water that we measured in the equator eventually makes its way up to the Alaska coastal current. It takes a long time. As I said, it's much more complicated. All along its way, it's interacting with other water masses and changing its temperature. But in general, it makes its way up to the Alaska coastal current, and that water in general is a little warmer than it has been. And then the Siberian coastal current so while the Alaska coastal current goes north, the Siberian coastal current kind of comes south, and they exchange water in the Arctic. And you can really see this here. So on this south side here is the Siberian coastal current, so it's colder, it's coming out of the Arctic. And then you have this warmer water on the north side here, heading north, which is the Alaska coastal current, which is a little bit warmer. But you can see the difference between these two water masses. Like this is much clearer blue, and this was kind of grayish, a little kind of murky. And here's what the temperature looks like. It looks warmer on the Alaska coastal current, and it's a little cooler as the Siberian coastal current comes down. Oh, I'm going the wrong way, sorry. There we go. There. So now we're in Kotzebue. Right here, here's that typical area that I mentioned where the ice is land fast, and it's there for throughout the winter typically. That's land fast ice. So that's ice that's attached to the land. And out here is what we call sea ice, or the marginal ice zone. So this is typical ice coverage in roughly April, say, or throughout, or most of the peak of the winter. Sorry. What we want to study is this region here. So this is the year, And this is the atmospheric temperature up in Alaska. So you can see here, most of the winter, it's right around 0 Fahrenheit. It's pretty cold. And as the spring kind of warms up, right around late April into May, you start to see this warming. It gets above freezing. So we wanted to go there right when it starts to get above freezing and study this melt. The area here in yellow is the region where most of the time, or most of the traditionally, when the indigenous communities would do their subsistence living and hunting in June, late May and June into July. So as I mentioned, here is this is what Kotzebue Sound looks like this past 2 years, where it was opened up earlier than normal. So there's the reason why they want to study, or we want to study sea ice, is that the marine mammals in the region use the sea ice to live. So in the wintertime, what are called ring seals build their dens in the ice, and that's where they pup and mate and live. And then in the spring, when it melts, there are bearded seals, and bearded seals don't really like to they like to live in the water, and they like to hop on the ice to sun themselves and warm up and mate just on the open ice. They don't build dens, they just kind of live on the ice. So, and they're not allowed to get into the sound until the ice breaks up. So in a time like this, the ice is all broken up and these bearded seals can come in and hop up on the ice. So when and how this ice breaks up, we want to understand when and why. So we measure the sea ice mass and momentum balance, and this requires local measurements of sea ice we employed or worked with the indigenous community to make these measurements. So the blue is what it was traditionally, the April sea ice coverage, as I've shown a few times, and the red is what it was in 2019. So it's open in the ocean, in the Kotzebue Sound region there. If we zoom in, there we go. So we zoom in, it's just a little more detail about the sea ice. Slow on here. There we go. So the Alaska coastal current comes in. There's also 2 rivers here, the Noatak and the Kobuk, and those kind of empty out into the sound as well. And one thing you'll see here, so here's the Kobuk coming down, here's a Noatak coming over. This is a satellite image of the landfast sea ice. You see this channel right here, and this channel is where the rivers empty into the sound. We're going to zoom in. So here's this channel right here. And we're going to instrument this channel, or we did, right in this region, to study how the ocean, the river, the atmosphere, what kind of roles they play in this freezing and melting of the sea ice. So we put a little measurements in the ocean at that red spot in the channel. And those measurements, so here's the ice on top of the ocean. There's some snow on top of the ice and the water below. We made all these little stakes. These are measurements of the thickness of the ice. That's what that measurement is there. So that we measure the thickness of the ice here. We put a mooring below the ice that measures the temperature of the water and how salty it is. We put measurements of the current beneath the water to measure the flow of the ocean underneath the ice. And we put measurements of the atmosphere here on the ice. There's a zoom in of those measurements. So it measures how much sun there is, how fast the wind is blowing, the humidity and the temperature. So from the ocean, coming up the channel, you get salty water from the ocean. And then from coming down the rivers, you'd have fresh water, typically. And in the water, there's a temperature gradient or temperature difference between the water that's right close to the ice and the water that's deeper in the river. And when the currents are strong, you get mixing of that temperature. So the temperature mixes up, and it that gradient of temperature from cold near the ice and warmer below gets mixed up and goes away. And that'll change how much heat gets into the ice. So here, one thing we observe is that, and this is in the, as you can see in the winter, in the dead of winter, whenever the temperature warms up, the salinity goes up. So the ocean is saltier, so the salty water is coming into the sound, up the river, up the channel, and it's bringing warmer water in. So you see these pulses of warm water that come in, potentially change or cause the ice to not grow as much. We also had measurements out here near the mouth of the, or not at the mouth, but at the opening of the entrance to the Kotzebue Sound. And we chose this region because this is kind of the pathway for this river and ocean exchange, as you can see by that little kind of diagram. So in the fall, at that ocean site, here's the ocean salinity in blue. You can see these spikes of this increases in salinity are the same times when we see these increases in temperature, just like we did in the river channel. So in the fall, a decrease in salinity is a decrease in temperature. And then in the spring, we see that decreases in temperature and salinity show increases in temperature. So what that means is that the rivers exert the primary control on the formation and the breakup of this land-fast ice. So the upstream river temperatures are likely to be useful as a diagnostic tool for anticipating whether there's a both freeze up and breakup of this land-fast ice. So one other thing we use the drones for up in Alaska. So here's a movie, here's the drone right there flying over the ice. So the usefulness of the drones is that you can go out, you can measure the ice properties without having to go out on the ice. At some point when the ice is breaking up, it's not really safe to be on the ice. So we can go out and make measurements using the drones and not have to be there. And that really helps us understand the process without being unsafe. So one that were observed was that, so this is the sea ice or the land-fast ice before the breakup. So we're able to measure everything here in this case. But then eventually right around this time in early May, we had to take everything out of the water because it started becoming unsafe. You can see the ice is opening up here, even more here. And then eventually the river channel completely opens up and this large piece of ice just breaks away. And so how does this ice surface change during the melt and the breakup? So while we're not out there, what's happening on the ice? And then how does this affect the exchange between the ice and the air? So we used the UAVs, the drones, to measure how much of that energy that we were, the sun is actually getting into the ocean and the ice, and either accelerating or keeping the sea ice growth to be what it normally is. So this measures both the thermal energy that gets into the ocean and the visible energy, the sun, that gets into the ice and then in the ocean. So we have both up and downward looking sensors, so that allows us to measure how much is coming in from the sun and how much is being reflected by the ice. And so you see here, there's a track along the channel, and you can see just even along this channel, you can see that how much sun is being absorbed by how much it changes just along this track. So there's much more sun getting into the ocean in this region than there is here. So there's faster warming of the sea ice here, and it's disintegrating faster here. And remember, that's where this big piece of ice broke away. And this is what it looks like on the surface. So there's this opening here where there's this more sun is getting into the ice and warming up the ice and breaking it up than there is over here. And eventually this spot is the spot where this ice breaks away, like right there, that location where it opens up, this just breaks away. So the point of understanding when the ice breaks up and impacts when the indigenous community can go on their subsistence hunts. So they hunt for these seals for their subsistence to live, and it's part of their tradition. So certain seals are there, need the ice to be there for their dens, and the other bearded seals need to have the ice there to broken up so that they can live on the ice and float around and mate and pump. And this is one of the local indigenous elders who has helped us throughout this campaign, and he was generous enough to help us or to take us out on some of his excursions during the hunt season. And one of the key things we've learned is that the number of days of the hunt, of their ability to hunt the ugaric or the bearded seal, has been decreasing over the last 20 years or so. So not only is the number of days of the hunt decreased, but also when that date occurs where it ends is becoming sooner, earlier and earlier in the season. So it used to be in the end of June, early July, and now it's even moving closer to the beginning of June, end of May. So in summary, traditional knowledge holders can greatly strengthen science through co-design of hypotheses. So when we went into the community, we discussed with them, or they told us what their interests were, and we built our science program around the interests of the local community. And we use UAVs for powerful, flexible platforms for environmental sensing. And the key thing is they can operate where human observers can't go in Alaska. And it allows us to make observations of physical processes connected to sea ice throughout the melt and breakup season when it's not safe to be on the ice. And I'll end it there and take any questions, but you can be happy to answer any questions after this in a week or months or whenever. You can send me an email, be happy to answer questions. I put up 2 websites. One is the Air to Sea project. That's all the work in Fiji. So there's a whole website on that. We also have a website for the Alaska project, Ikavik Sikakun, Kotzebue, Alaska website. I have a bunch more videos on my lab webpage or video page. And you can follow us on Twitter at these tags. And I'll take questions.
Great,
Any more
thanks,
questions?
Chris. Yeah, so we have 2 questions. I encourage our participants, since we have plenty of time, here's a great opportunity to get Chris, who is very busy, to have his full attention here. And it's so these are 2 great questions to get us started. So first off, we have a participant who's interested in hearing about how you got into your current role.
Wow.
Yeah, and if you could walk us through your career a little bit, that'd be great.
This is a great question, and I actually love talking about it. For me, I grew up in Boston, Massachusetts, and I've always loved being on the ocean. And any chance I got, I would go up the coast, go out on the beaches. Anytime I could get on, one of my friends had some dinghies. We'd go out on a boat and just hang out on the water whenever I could. So from a young age, I loved being on the ocean. And I also had a love of just kind of math and engineering and science. But I never thought about being an oceanographer until I was even in college. I had no idea that there was even, you know, this field of oceanography. And then in high school, I just loved doing math and science. And in college, I was an engineer. So I really started to tinker with instrumentation. And I don't know if you got an understanding, but I like to tinker with cool sensors and equipment. So that's kind of something that stuck with me throughout my career. But then I went to grad school, and I went there to do engineering. And I remember the first week I went there, my advisor said, "Oh, there's this great project over in this lab to use an infrared camera to look at breaking waves." And I'm like, what are breaking waves, and what's an infrared camera? So I went over to talk to this guy, and that opportunity came up, and you know, I took advantage of opportunities as they came up along the way. So, you know, I didn't really have this vision that I was going to be an oceanographer. I just had a love of science and math and engineering that kind of opened doors for me along the way. Yeah, and then every time I went to a new location, I kind of expanded the things that I worked on. So when I was in grad school, I studied small scale waves on the ocean. When I went to my postdoc at Woods Hole, I started studying about estuaries and carbon fluxes and how important it is in coastal areas to study carbon uptake and the carbon cycle. And then when I went to Lamont, when I first started there, I got to go up to both the Antarctica and the Arctic and doing projects in places I hadn't done before. So how did I get the job? It's it was been lucky along the way to do what I love, but take advantage of opportunities when they arose. I think is the key thing for me, and maybe for a bunch of people in my profession. And then, how interdisciplinary is the team? Are the UAVs built by your team? So the first part of that question, how interdisciplinary? So both teams, so the team in Fiji is very interdisciplinary. There are engineers that fly the aircraft. There are engineers that maintain the aircraft. There's engineers that build and maintain the sensor systems. There are scientists that study oceanography. There's scientists that study atmospheric science. There's scientists that are microbiologists that study the cyanobacteria itself. So there's a whole host of disciplines that all work together. And the same thing in the Arctic program. Same types of, I'd say the same groups of people there. And then in addition, we have marine mammal experts. And then are the UAVs built by my team? No, we build the sensors that get put on right up here in the front of this. But this UAV itself is built by a company in Arizona called Latitude Engineering. And they build these UAVs and other types of UAVs. And they're not inexpensive. These are pretty expensive instruments or aircraft themselves.
Great, thanks, Chris. So I have a question.
Sure.
While I think I'll give another opportunity to our participants to ask any additional questions. So how, from your point of view, and I think I know the answers to this, but how important is sort of technology and creating or retrofitting current technologies to continue climate research, especially in hard to get to places, and why those hard to, and why do you think we should be studying those hard to get to places, and where does technology fit in to that research portfolio?
So I think that what in general, that the UAVs provide a new way of doing research, oceanographic research, any research, in that when you're out on the ocean, let's just take the ocean for instance, when you're on a ship, you're out there for say 30 days on the ship, 30 to 60 days. And you go to a spot, you have some idea of where you want to be, and you put instruments in the water and things come by, you watch how the ocean changes. If you really want to target something, which we were able to do in this Fiji experiment, is the UAVs, we were able to basically send them out on a mission, find what we're looking for, and eventually, once you find it, you can mobilize the ship to come to where that location is. So it's a much more efficient way of doing research, because rather than just sitting in a spot and never seeing what we want to study, you're able to use the drones to go find what you want to study and map it out and have all your equipment in the water right there, and getting the measurements that you need to understand the science. So it's really kind of a transformational, groundbreaking way of doing research, which is, I hope it catches on for more oceanographers than just myself, because it's a great tool to have as part of the oceanographic fleet. And then the beauty of it as well is that while we put certain instruments in these payloads, we can put any instrument in there. If it's small enough and you can design it, we can put it on there. So it's really a great platform in general to expand how we do science.
Great, thanks. And you talked about using the RV Falkor as kind of home base. Can you talk a little bit more about what it's like to do research aboard a vessel like that? Sure. the fun things, the not so glamorous parts, and how long are you out there for when you are on these ships?
So I'm going to zoom back to that, but while I'm doing that, so the Falkor is actually a very, very nice ship to work on. It is kind of state-of-the-art, very almost, I wouldn't say luxurious, but in terms of other places I've been on, other ships I've been on, it has all the amenities that you could ask for on a ship. So that being said, being on a ship, it's like being in a dorm in some ways, where you're sharing kind of bunk space. So everyone, you may have 2 or 3 people in a room, and you share you don't share beds, but you all have a different bed in a room, just like you would a dorm. You share a restroom and a shower. There are specific meal times throughout the day. If you miss the meal, then you don't get, you missed the meal. Let's see. When you're working, the spaces are rather small. You saw the one, I'm trying to get back to the one spot. You don't have to break out, it'd be easier. The one spot on the ship where we're in the mission control, you saw there were like 10 people in that one space. It was very crowded. And that's what it's like on you'll have spaces like this that are very crowded, confined. And the ship is always moving. So you spend a lot of your energy just trying to stay upright. And you're at sea for like 30 days to 60 days. And all you see is this. All you see is water and sky for 30 days. You hardly ever see any land. But we do have the ability to be online. So we're on the web, but it's not very fast. But it allows us to get data from land, from satellites, so we can target some regions that we want to go to. and also communicate with people on land in terms of doing the experiment and the science design.
Okay. Great, thank you. So we've had two questions pop up.
Yep.
First, so, you know, has COVID suspended the research, and what are sort of some of the next steps, I guess?
So luckily for us on the Fiji project, the project is, we've made all the measurements. So we've been out to sea, and now we came back before COVID started. And for that project, it hasn't really suspended the research because now we have all the data and we can work on the data from home or from the lab when we get to go back to the lab. But from home, we're able to work on all the data. For the Alaska work, we did finish the main parts of the measurements last 2 years. So we're able to look at all the data again as well. And so it hasn't really impacted that research. What it has impacted is our ability to go back and meet with our advisory council, the indigenous elders and the community to kind of, you know, have our discussions. So that part of the research has kind of been slowed a little bit, but we hope to get back there in next year at some point. Let's see, what is the best adventure you've had in all of my profession? Best adventure, you know, I must say that anytime I go to sea is an amazing experience. I love going to sea, and every time it kind of just reminds me how appreciative I am of being an oceanographer and to be able to do what I do. So each one is an individual adventure, and I wouldn't put any one of them above another one, really. Yeah, I can't think of anyone that stands out really because they're all just so amazing. Let's see, what's the other one? Do I work with volcanologists? So that's a very good question. And we do work with some volcanologists. For our purposes, we want to understand how, so the volcanologists want to understand what the material is that's on the surface. For me, I want to understand how, getting back to that original question, the volume, how much spatial scale do these pumice patches, how large are they? And then how much do they warm the ocean? So those are my main interests, are physically, how much do these pumice patches warm the ocean, just like cyanobacteria warms the ocean? How much does it impact that?
Great, thank you. So I think that was the end of our questions, and it's sort of perfect timing because it's 2:59, and I want to respect everyone's time for tuning in here. Chris, thank you so much again. Any sort of parting words or messages for our folks watching? We'll definitely share all the links that you have shared,
Yep.
including the links to your site for additional videos, as well as your contact information in case anybody has any questions. But just wondering if you have any last words.
Just feel free to contact me. I know Cassie said that I am very busy. I am, but I do love to engage and you know, discuss what we're doing beyond these events.
Okay.
So feel free to give me an email anytime.
Excellent, thank you so much. So to our viewers, we will share a recorded link to the session along with all of the resources that Chris has shared with you in a couple of days, definitely by the end of this week. And you can go back and watch the recording whenever you'd like. So as I mentioned at the beginning, this is the last EI Live K-12 session for this semester. We will do something in the fall. We're not sure what that looks like yet. We have some ideas and several contingency plans, just like everybody else when it comes to our programming for the fall, but stay tuned. If you'd like to remain on our contact list, just email me directly. I'm happy to keep everybody in touch about what's going on. So thank you again, Chris, and thank you for tuning in for our last session here. And hope everybody has a good rest of the day. So thank you.
Thank you, Cassie.
All right.
And thanks to everyone who joined in. It was really great to have you. Thanks a lot.
Yeah, great. Thanks.